design of this AB in the left. Now, if and
Hello students, welcome to my YouTube channel VRacademy, and where we are studying various electronic subjects, and we have started with digital electronics, and today's topic of discussion is magnitude comparator. So let us begin the analysis of magnitude comparator. As I have said you, that whenever we are going for designing or defining any type of device, we are always taking the help of its name, and from the name itself we are deriving all the things. Okay, so the name is magnitude comparator. Okay, magnitude comparator. So it is as the name is suggesting, it is comparing the magnitude of two binary numbers. So basically, when we are going for the definition, we have to just keep two things in the mind, that what exactly magnitude comparator does, and what are the outputs that we are expecting. So it's a simple concept. You can take the help of a normal example. Let us suppose I am taking two lines. This is A, this one is B. Similarly, we'll take a line that is P and Q. If I'll ask you, just compare the magnitude of A and B, AB, line AB and PQ. You can clearly say that line AB is smaller than PQ, or we can say that PQ line is having greater magnitude than line AB. So this is what the comparison is. Now, similarly, if I can take this line that is CD, and if I will ask you what about CD, then you can say that line CD is equivalent to AB. So therefore, the conclusion is that when we are comparing the magnitude of any two things or any two numbers, we are expecting three output. What are those? Those are greater than, equal, or less than. So these are the things that you have to keep in mind while going for the definition. You have to keep two things in the mind. The first thing is that it is a combinational circuit that compares the magnitude of the two numbers, two binary numbers, and it produces greater than, equal, or less than as the output. Now, if you will combine these 2 points, you will get the definition of the device. So now, if anyone will ask you about the definition of the magnitude comparator, you can say it as that it is a combinational circuit that compares the magnitude of the two binary numbers, and it produces three output, that is greater than, equal, or less than. Now, depending on this, we are having, or we have to study in digital electronics, we are having three basic types of magnitude comparator. Those are 1-bit magnitude comparator, 2-bit magnitude comparator, and 4-bit magnitude comparator. The name is given on the basis of how many number of bits are present in the numbers that we are taking in consideration for comparison. So that is why the name is given like this one. Now we'll try to study all of them one by one, and we'll try to study about their definition, their design process, and the actual design. We'll go for 1-bit magnitude comparator, 2-bit magnitude comparator, and 4-bit magnitude comparator. Now starting with 1-bit magnitude comparator, as I have said you previously also, that it compares two binary numbers that consists of only 1 bit. I mean, it takes input as two binary numbers, and each of the binary number will have only one binary bit. That is what I want to say. So this is the definition. Now we will go for the design directly, and we know the design process of any of the combinational circuit is fixed. As I have said you, that will not migrate from what we are doing previously also. So here we are having two inputs. I am taking those inputs as A and B. These are the two numbers, and because they are of only 1 bit, I am taking them as A and B. Now, what are the output expected? There are three output expected, as I have said in the definition. One is greater than, other one is equal, and third one is smaller than. Okay, so this is your 1-bit magnitude comparator. This is your 1-bit magnitude comparator. Now, once we are done with the block diagram, we'll move ahead with the truth table. So this is next truth table. Okay. Now, as I have said you, in order to make the truth table, we have to first consider the inputs. So what are the inputs? A, B. Now, if there are two inputs, we know that the total number of combinations that are possible are 0, 0, 0, 1, 1, 0, 1, 1. And let us suppose someone wants to write it as 0, 0, 1, 1, 0, 1, 0, 1. That is also fine. Now, what are the various outputs expected? The outputs are, first one is G, then E, and then last one is S. GES represents greater than, equal or smaller than. Okay. Now, I have said you that whenever we have to fill the output of any combinational circuit or output of truth table of any combinational circuit, we have to take the help of its definition or the explanation of the device. So what is the definition of the device? It compares both the binary numbers. So comparison is to be done in A and B. So I'll go on comparing it. So 0 comparison with 0. Definitely both are equal. So we'll have 1 at equal and both G and S will be equal to 0. Okay. Similarly 0, 1. So you can see that 0 is smaller, B is greater. So it will activate S and we'll have 0, 0 to the G and E. Similarly 1, 0, here we can find out 1 is greater. So we'll go for greater than, the other two outputs are 0. And simultaneously when we are going for 1, 1, we are finding out both are equal, both bit are equal. So we'll have 0, 1, 0 as your output bit. Okay. Now once we have got this, after that I have said you to go for what? Go for writing the Boolean expression for each of the output in terms of input. So first one is Z. So for G, you can clearly see G is higher at this position. And what is the value of A and B at this output? The value is 1 and 0. So when we are going for writing the SOP expression, we'll be writing it as A, B bar. Why A, B bar? Because A is 1, B is 0. So therefore A, B bar. Next, we'll go for writing the expression for E. It is equal to, we can see that here equal output is 1 and here also it is 1. So we can have the summation of these two values. So here you can see that the value of A and B is 0, 0 while A and B is 1, 1 over here. So we'll have AB plus A bar, B bar. Now this value AB plus A bar, B bar is nothing but A XNOR B. The last one is S. So for S, you can once again see here we are having 1 at only one position, and at that time the value of A is 0 and B as 1. So definitely it will have the value or Boolean expression as A bar B. A bar B. Now once you have got this, you need to go for the design, because when we are going for 2-bit magnitude comparator, whatever output we are getting, that is already in a reduced format. So we need not have to bother for the reduction. We have to directly go for its design. So let us go for its design. Now for designing this, I'll tell you a process, a method. For designing this, you have to follow a method so that this design will look very peculiar, and you will be able to learn that whenever we are going for designing the magnitude comparator of higher bit, how we'll be doing that. This design is going to help you in going for higher bit magnitude comparator design. So for that, we'll go for that process which I am telling you right now. Okay. So whenever we have to go for design, the first thing that you will design is E. The first thing that you will design is E. And we know that the value of E is A XNOR B. So first I will go for A. This is our A. And this one is B. This is your B. Just take the XNOR of both A and B. XNOR of A and B. This will give you E output. This is your E output. Now once you have got E output, next you have to go for G. Or S you can go depending on your choice. But whenever you are going for G, it has to be drawn above E. And whenever you have to draw S, it has to be drawn below E. Why? Because it is general perception of a human being that greater numbers are always at a higher position, smaller numbers are at lower position. So that is why we are going to draw G at the top and S at the bottom. So what is the value of G? A, B bar. So just take A from here, take A from here, take B from here, and since B is with bar, just connect a NOT gate over here, connect it with AND gate, and this output is nothing but your G. After doing this, we have to go for S. What is the value of S? S is equal to A bar B. So we'll take A once again and we'll take the bar of that one. So bar means we have to connect a NOT gate over here. Similarly, we have to go for B. So just take B from here, connect it with this. This is your AND gate. After that, just put up this, extend this line. This is your S. Okay, so now you can clearly see if I am blocking this, okay, I have blocked this, okay, and now you will be able to understand that it has two inputs, A and B. Here also we will just have a comparison and see this is A and B, this one is also A and B, and here we are having three outputs G, E and S. Here we are having three outputs G, E and S. The pattern of drawing is fixed. If you will be keeping it fixed, it will be helping when we are going for the design of higher magnitude comparator. So this is how 1-bit magnitude comparator is designed. I think it is, I mean, all of you must have understood this. Okay, so after this we'll be moving to 2-bit magnitude comparator. Now, as per the instruction that I have given you, that the names are given on the basis of the number of bits that are present in the binary numbers that we are comparing. So when we are going for 2-bit magnitude comparator, it compares two binary numbers having 2 bit each. Means each of the binary bits or each of the binary numbers will have 2 binary bits inside that one. Now, in order to have the design of this one, we'll take the help of this 1-bit magnitude comparator, and we will also have the general knowledge of comparison. By using that one, we'll have the design. Now, you can ask me, sir, why we are going for such method, why we are not following this, that is normal design, the block diagram, truth table and all. Because if we are going for that, for 2-bit magnitude comparator, it will have 16 combination, and then we have to go for 16 combinations and all. So that will become a tedious task or acute task. But if we are going for a normal method, as I am insisting you, you will be able to learn each and everything very easily and lucidly. Okay, so let us start it. Now, first tell me, if I am comparing these two numbers, 76 and 53, okay, and if I will ask you which number is greater, by default you will say that 76 is greater. Why? You will just have the comparison of their tens place number, that is 7 and 5, and if you are finding out that if the tens place number is greater, the number is going to be greater, isn't it? Similarly, if I will tell you to have the comparison of 52 and 46, you can say here that which number is smaller. So directly you can say 46 is smaller. How? Just by comparing the tens place number. Now, this is one process by which we can know a 2-bit number is greater or less. I mean, just by knowing the tens place, we can say that the number is greater or smaller. If the tens place number of the given number is greater than the tens place number of the other number, then definitely the first number is greater. Similarly, we can think about the smaller number also. So if the tens place number of the given number is smaller than the tens place number of the other number, then the first number is smaller. So similarly, by using that perception, we can say the greater than and less than. Now, one more context will be there. If I'll write 59 and 56, then once again if I'll ask you which number is greater, so you can once again tell कि 59 is greater, 56 is smaller. How? You have first compared this tens place number and you found that both the numbers are equal. So what you will do, you will just move to the unit place number and you will have the comparison. And if you find out that the unit place number of the first number is greater than the unit place number of second number, then you can say that that number is greater. So we are in the diversified space where we are having two conditions. The first condition should be tens place should be greater, and second condition is tens place should be equal and unit place should be greater. This is the condition to become a greater number in case of 2-bit number. I think it is gettable to everybody. I mean, you must be understanding that. Similarly, if I am going for 55 and 55, if I'll ask you what is, just do the comparison of these two numbers. So you can clearly say कि both the numbers are equal. Why? You are comparing the first tens place and tens place of the second number, unit place of first number, unit place of second number, and you are finding out everything is same and equal. Then you can say that both the numbers are equal. So genuinely, we'll be utilizing this concept in order to design this 2-bit magnitude comparator. Now let us see how I am doing it. Okay. So for design, I have taken the first number as, this is my first number, I am taking the first number as A1, A0, and second number as B1, B0. Okay. Now we'll have the comparison. Okay. Now, if I will ask you, tell me the condition in which first number is greater than the second number. Okay. So, condition for first number greater than second number. What are the conditions? This is the thing. Once you are finding it out, you will be able to write the expression in a single moment. Okay. So you see, first number will be greater if a1 is greater than b1, then automatically it will become greater, isn't it? This is what I have said you right now. So the first condition will be for g part, I can write a1 can, if a1 is greater than b1, then we are having greater number. Okay. Now, other than this, what are the possibilities? It might be possible that a1 can be equal to b1. Then in that case, where we'll jump? We'll jump at a0 and b0. And if a0 is greater than b0, then also we can say that the number is greater. So the second condition will be either this or a1 equal to b1 and simultaneously and a0 must be greater than b0. I think you have got this. I think you got this. This is the thing. This is the beauty of this line, what I have written. If this is greater than this, then number is greater. If this is equal to this one and simultaneously this one is greater than this one, then the number is greater. So I think it is, you have got it. Now once you have got it, you will be able to write the Boolean expression very easily. A1 greater than B1. Now look at this one. A greater than B. What was the expression? AB bar. Now here it is A1 greater than B1. So I can write A1 B1 bar. We can write like this. Just compare this with this, you will be finding out the answer. Now, alongside this, or means we have to put a plus sign. Then A1 equal to B1. For equal, you can see that it is A XOR B. Here it is A1 equals to B1. So we can write A1 XOR B1. And after that, we have to go for a AND expression. That means we have to put a dot and A0 greater than B0. So similarly, as we have written it over here, we'll write it as A0 B0 bar. So this is the expression for G. I think you have got it. This is the thing. So conditions once we have written this condition, we'll be able to write the Boolean expression. Similarly, what is the condition for first number equal to second number? What is the condition? Any one of you can suggest or write in the chat box what is the condition for first number equal to second number. So for first number equal to second number, you have to look for a1 equals to b1, a0 equals to b0. So how it is possible? We can write it as e equals a1 equals to b1 and simultaneously a0 must be equal to b0. a0 equals to b0. Now condition a1 equals to b1 and a0 equals to b0. We'll just have the comparison from this one bit comparator and we'll be able to write the expression. So e equals to a1 XOR b1 and a0 XOR b0. I think you have got this. This is very simple. Both the numbers are equal, so this should be equal to this should be equal to this. That is what I have written. And because equal condition is satisfying A XOR B, therefore we have written it A1 XOR B1 dot A0 XOR B0. Now the last one is condition for first number less than second number. Okay, first number less than second number. So what is the condition? Once again the same process. Yes, either a1 should be less than b1. This is the first condition. So a1 must be less than b1. This is the first condition. Or what is the condition? Both should be equal. That is a1 equal to b1 and simultaneously and a1 must be less than, a0 must be less than b0. So once you have written this condition, you will be able to write the final expression, that is a1 b1 a1 bar b1, or means plus a1 equals to b1 means a1 XNOR b1, and means you put a dot and then a0 bar b0. So this is the expression for S. So just number it. This is your equation number 1, this is your equation number 2, and this one is the equation number 3. Now by using 1, 2 and 3, we'll be able to design the magnitude comparator. Now I think you have got this expression. It is perfectly alright, and using the normal concept we are able to derive this Boolean expression. Now once we have derived the Boolean expression, the next journey is to draw the diagram, and I have said you this is the most important part for drawing the diagram. It is very important that you should learn a process which I am insisting you. I mean, using that one only you will be able to design, okay, and you will be able to design it correctly without any hesitation. Okay, so once again, for drawing this G, E and S, the first thing is that you have to draw the E value first. So for drawing the E value, we'll just go for the process. This is our A1, this one is B1, so I'm going for these two. I'm taking a XNOR of both A1 and B1. Similarly, I'll take A0, B0, and we'll have XNOR of both of them once again. Okay. Now, after XORing, you can clearly say A1 XNOR B1, A0 XNOR B0. After XNORing that one, we have to go for ANDing them. So we'll go for ANDing them. We'll just take like this, AND them, and we'll get the output as E. Okay. So this is the first thing that you will draw. I mean, you have to draw the E part first. The output E should be drawn first. Now once you have drawn the E part first, what you will do, you will draw two AND gates, two AND gates at the top. This is the first AND gate, this is the second AND gate. Similarly, you will draw two AND gates at the bottom also. One AND gate over here. And why I am drawing it, I'll let you know why I am drawing it and what is the reason for doing that. Okay. Okay. So once you have drawn these two AND gates at the top, AND gates at the bottom, both these AND gates are going to be utilized for G, and this is for S. Now how it is? Just here you write down A1, B1. Here you write down A0, B0. Similarly, here you write down A1, B1, and here you write down A0, B0. Now, after that, you will just see the expression of G and try to design that or draw that one using these two AND gates. So first of all, the first part of this G is A1, B1 bar. So A1 is as it is, so I will take A1 from here. I'll take a connection from here, A1. I'm taking the connection of A1 from this, okay, and B1 bar. So I'll take B1 from here, okay. Now since it is bar, so we'll connect a NOT gate over here and connect this to this. The output of this is going to be A1, B1 bar. This is your A1, B1 bar. Now after that, the second part need to be drawn. So for that, you can see that A0, B0 bar is there, but alongside that, A1 XNOR B1 is also present. I mean, this output is also present over this AND gate. So we'll have a connection of this to this output. We'll have a connection of this to this output. And for A0, we'll have the connection like this one. We'll have the connection like this one. And for B0 bar, we'll have the connection like this. Now once you have done this expression or the output of this AND gate is going to be A1 XNOR B1 whole multiplied with A0 B0 bar. I think you have got this. So this is the second part, this one is the first part, and both of them are connected with which gate? OR gate. So connect them with a OR gate, connect both of them with a OR gate, and you are going to get the G output. Okay, this is your G output. Similarly, for the bottom part or for S part, you can see that the first output is, or first part of this output is A1 bar B1. So we will take A1 bar B1. So from here you will have a connection, just put a NOT gate. This is going to be A1 bar, A1 bar, and from here you will take B1 and connect this to this. This is your A1 B1 bar. Sorry, A1 bar B1. Now once you have that connection, you look at the second part. Once again, we are having A1 XNOR B1. Along that, A0 bar B0. That means we have to take the help of A1 B1 bar. So for that, once again, we'll take the help of this line and connect it to this AND gate. And A0 bar should be connected like this one. This is your A0 bar, and this one is B0. This one is B0. The output of this one will be A1 bar B1, and the output of this one, you can see that I have taken it from here. So it is A1 XNOR B1 whole into A1 A0 bar B0. Now the output of these two, this is the first part, this one is the second part. It is connected with a OR gate, so we'll have the connection it with OR gate, and this will give you the S output. Now you can see that the design is very clumsier. I mean, if you are going for normal drawing of G, E and S without using this method, you will be able to design it, but your design will become very much clumsier and you will not be able to signify it, or you will not be able to show it clearly. But here you can clearly show to the examiner that here we are having two binary bits, two binary numbers having A1 B1 as the input and A0 B0 as the input, and it will produce three output, that is G, E and S. So this is about 1-bit magnitude comparator and 2-bit magnitude comparator. I think you have got this one. Okay, but your design will become very much clumsier and you will not be able to signify it, or you will not be able to show it clearly. But here you can clearly show to the examiner that here we are having two binary bits, two binary numbers having A1 B1 as the input and A0 B0 as the input, and it will produce three output, that is G, E and S. So this is about 1-bit magnitude comparator and 2-bit magnitude comparator. I think you have got this one. Okay, so thank you for now. We'll take a leave and we'll be discussing about 4-bit magnitude comparator in the next class. Thank you for joining.